1922. 67 tons of riveted American steel rolled beneath the cranes. 1,100 horsepower waited inside 4 traction motors. 1,500 volts ran through copper windings, circuit breakers, and control gear powerful enough to drag a loaded passenger train out of Tokyo, and powerful enough to kill a man before anyone saw smoke or flame. These were American beasts. Baldwin forged the frames in Pennsylvania. Westinghouse built the electrical nerves near Pittsburgh. One company shaped the steel, the other trapped lightning inside it. Together, they produced locomotives unlike anything Japan could yet build for itself. Boxy, black machines that could accelerate faster than steam, climb into service without a firebox, and move traffic through the busiest railway corridor in the country without choking stations and tunnels in coal smoke. But machines like these never came cheaply. In America, men poured molten metal within feet of their boots. They stood beneath locomotive frames hanging from chains rated for tons. They filed castings by hand until their fingers locked stiff. They tested electrical equipment carrying enough current to stop a heart in silence. One bad lift could crush a crew. One broken chain could turn a shop floor into a grave. One mistake behind a live switch could leave no warning at all. And the factories building these locomotives already knew what industrial ambition could cost. Only 5 years earlier, an explosion on the same sprawling Pennsylvania grounds had torn through a wartime plant and killed 133 workers. 55 of them could not be identified. They were buried together because the blast had left no names to attach to what remained. That was the world these locomotives came from. American steel, American electricity, American scale, and American workers standing close enough to the machinery to pay when anything failed. So what did it actually cost to build the finest electric locomotives America could export? Who paid that cost? The Japanese government signing the order, the American companies collecting the money, or the men beneath the cranes and beside the furnaces? What were these machines expected to accomplish once they crossed the Pacific? Why did Japan buy American locomotives when British, German, and Swiss builders were offering machines of their own? And why, after the American machines proved themselves among the strongest and most capable in the entire imported fleet, did the follow-up orders never come? The answer begins on the docks in Japan, where engineers were waiting for more than transportation. To Baldwin and Westinghouse, these locomotives were finished products. Contracts completed, machines built, tested, shipped, and paid for. To Japan, they were the beginning of something America had not been told about. Because the greatest danger to the men who built these beasts was not only the furnace, the crane, or the 1,500 volts running through their work. It was that America had just sold Japan machines valuable enough to study and powerful enough to make the next American order unnecessary. The autopsy nobody announced. Start with the number that should stop you cold. In 1889, 1 out of every 117 men working on an American railroad did not live to see the next year's paycheck. Not hurt, not maimed, dead, on the job. Every year, like clockwork, like a tax the industry collected in bodies instead of dollars, and nobody with the power to change it seemed to be in a hurry. And if you worked what railroaders called the running trades, the men riding the tops of moving freight cars, climbing between couplings while the train was still rolling under them, your odds got dramatically worse. 1 in 12 of those men could expect a career-ending injury in any given year. A sitting United States congressman stood up in 1892 and compared it to war. He said, "Railroad men suffered like soldiers fighting a battle, minus the uniform and minus the medals." By 1900, national reporting still put the death rate at 1 in every 399 railroad employees per year, and the injury rate at 1 in 28. Improvement, technically, still a slaughterhouse by any modern measure. The single deadliest task on the whole railroad had nothing to do with fire or steel rail at all. It was standing in the gap between 2 rolling steel cars with a metal link and a loose iron pin. waiting for the cars to slam together close enough for a man to drop the pin home by hand, and praying his fingers cleared the gap before the steel did. In 1888 alone, that single motion killed roughly 300 American railroad workers and mangled 6,700 more. Nationally, coupling accidents accounted for something like 43% of all reported railroad injuries and close to 1 in every 5 deaths. This particular brand of arithmetic was distinctly American, too. Comparable British railway workers, on a smaller, denser, more heavily regulated network, died at a noticeably lower rate across the same years. Vast distances, thinner traffic, and cheaper construction had pushed American carriers to economize on both machinery and manpower, and the men paid the difference in fingers, hands, and lives. We are not explaining why that was allowed to continue for so long. Not yet. Just sit with it. Now scale the danger up to industrial size. One single American company, the one whose steel would eventually ride under a foreign flag on the other side of the planet, could turn out 3,000 locomotives a year from a single Pennsylvania site. 3,000. In 1 year, from one factory complex. And that same company, within a single 12-month stretch, watched its own workforce crater from 18,499 men down to 4,600. Because the American locomotive trade ran on booms and busts as violent as anything the machines themselves produced. An empire that could hire that fast could gut itself just as fast. It would do exactly that more than once. Here's a fact we are not explaining yet either, and it's the darkest rung on this ladder. On one April morning, inside one American factory complex, the very same grounds that would soon manufacture the mechanical bones of the machine at the center of this story, 55 men and women died, with no name anyone could attach to what was left of them. They are buried together today, in a single grave that lists no individual names, because there was nothing left to identify. Hold on to that fact. We are coming back to it, and it is worse than it sounds right now. One more rung before the strangest one. The electrical half of this story was built inside a Pittsburgh factory complex so large that, at its peak, it employed something like 22,000 workers under one roof, a small city's worth of men working with equipment carrying enough voltage to kill in total silence. No flame, no smoke, no warning at all. Danger, on that floor, didn't announce itself. It waited behind a switch. And now the strangest fact in the whole story, the one this entire video exists to explain. Starting in 1922, the Japanese Ministry of Railways spent real money on 59 electric locomotives from manufacturers across the United States and Europe, and had no intention of running them forever. Engineers measured every gear ratio. They traced every wire inside every circuit breaker. They copied frame dimensions down to the rivet pattern. Within roughly 6 years, Japan built its own version from scratch, and the imports were finished in their frontline role for good. Two of America's biggest industrial rivals, companies that had spent decades trying to bankrupt one another in the open market, ended up bolted into the same foreign engine, and neither company had a vote in the matter. That's the machine. That's the mystery. Everything else in this story is the explanation you're owed. Chapter 2. The Company That Forged the Knife. The reason coupling killed so many men for so long comes down to plain arithmetic, and that arithmetic favored the railroads over the men doing the actual coupling. For decades, American railroads ran almost entirely on link and pin couplers, a loose iron link and a hand-dropped pin, the cheapest possible way to join two rail cars, and a design that required a human hand in the gap every single time two cars met. An inventor named Eli Janney patented a safer knuckle coupler that let cars lock automatically without a hand ever entering the danger zone. As early as 1873, railroads mostly ignored it for the next 2 decades because retrofitting an entire national fleet cost real money, and nobody wanted to spend first while competitors didn't. Only after Congress forced the issue with a Federal Safety Appliance Act did automatic couplers become standard equipment. And only then did coupling's share of the death toll finally start falling, down to a fraction of what it had been by the turn of the century. That's the first debt from Chapter 1, paid in full. Those men died for the price of somebody else's spreadsheet, delayed by 2 decades of pure cost avoidance. Now the company that built the knife Japan would eventually use to cut its own path forward. Matthias Baldwin started out as a Philadelphia jeweler and whitesmith, a man who made his early living on bookbinders' tools and printing cylinders, not a trained mechanical engineer by any formal measure. By 1831, he had a small demonstration locomotive running on a circular track for a crowd of city onlookers who had never in their lives seen anything move under its own power before, hauling 2 miniature cars, fitted with seats for 4 passengers apiece, around and around, while the crowd pressed in to watch. The business he founded grew for the better part of a century, through booms, panics, and 2 world wars, into the largest locomotive manufacturer on the planet. By the 1910s, the company bearing his name had outgrown its cramped city blocks in Philadelphia entirely, and was pouring money into a new complex at Eddystone, Pennsylvania, 616 acres along the Delaware River, eventually capable of turning out more than 3,000 locomotives a year. That capacity is exactly the number from Chapter 1, and here's the rest of that debt. The same company that could hire that fast, cutting its own workforce from 18,499 men down to 4,600 within a single year, had just been slammed by a nationwide financial panic in 1907 that gutted new orders overnight. Boom and bust was simply the business model, and the men on the shop floor absorbed the volatility every time it hit. This was the plant that would build the mechanical bones of the machines Japan later came to study. And, 5 years before those machines existed, the same grounds would earn a much darker kind of attention. Keep that in mind. We'll come back to it. But steam wasn't the only trade Baldwin worked. As early as the 1890s, Baldwin had already partnered with a Pittsburgh company called Westinghouse Electric to build small electric locomotives for mines and industrial yards, years before anyone in Tokyo had reason to care. Westinghouse itself had started in 1886 with barely 200 men in a small Pittsburgh shop, founded by George Westinghouse and staffed early on by engineers whose names would end up in physics textbooks: Nikola Tesla, William Stanley, a young mechanical engineer named Bertha Lamy, who became the first woman to hold that title professionally in the country. By 1904, the company employed 9,000 workers at its main East Pittsburgh plant alone, with 3,000 more scattered across branch factories, inside a facility so enormous that its main production aisle ran more than 1,100 feet end to end, longer than 3.5 football fields laid nose to tail, patrolled overhead by traveling cranes strong enough to lift a locomotive frame the way a man lifts a suitcase. Baldwin built the muscle. Westinghouse built the nerves. Between them, by the 1920s, the 2 companies had built one entire half of America's electric locomotive business. The other half belonged to 2 different rivals entirely. General Electric, formed in 1892 out of a merger between Edison's own electrical company and a competing firm, and running its own enormous works out of Schenectady, New York, and the American Locomotive Company, universally shortened to ALCO, itself stitched together in 1901 from a handful of smaller locomotive builders and headquartered in that same city. Different frame geometry, different electrical philosophy, a completely different corporate culture, sitting in some cases only a few miles from its rival's front gate. GE and ALCO spent decades trying to outsell Westinghouse and Baldwin in every market that mattered, at home and overseas, in a rivalry as real and as bitter as any in American industrial history. Which is exactly what makes what happened in Japan so strange. Japan didn't pick a side in that rivalry. Japan bought from both camps, and then built something neither American company would ever have designed on its own, and neither would have agreed to build together even if you'd paid them. Here's the actual problem the Ministry of Railways was trying to solve, and it was as concrete as problems get. Japan converted the Yokohama to Kozu stretch of the Tokaido line to 1500-volt direct current power beginning in 1922, then extended electrified operation through to Tokyo Station itself the following year. Ridership on that corridor kept climbing faster than steam power could serve it, and every delay compounded down the line. Because the Tokaido corridor stood as the single busiest artery in the entire national network, carrying a wildly disproportionate share of the country's rail traffic through a narrow stretch of track that steam locomotives were straining to clear on schedule. Electrification here amounted to survival math for a rail network trying to keep pace with a capital city that refused to stop growing, on a corridor that could not simply be widened or duplicated fast enough to solve the problem any other way. So the ministry went shopping, and it went shopping in 3 separate batches, sourcing locomotives from Britain, from Germany, from Switzerland, and from the United States. A genuine international bake-off, whether the competing manufacturers realized they were entered in one or not. And almost immediately, the Japanese engineers running acceptance trials noticed something the sales brochures hadn't advertised. The American machines were the standouts of the entire fleet, ahead of the British, German, and Swiss designs sharing the same tracks. 2 American lineages in particular earned that reputation, one built by Westinghouse and Baldwin working together, another built by General Electric and Alco working together. Neither batch had been designed with the other in mind. Neither American company expected a foreign customer to treat their locomotive as a textbook instead of a purchase order, let alone to quietly rank it against European rivals and declare it the winner. There's an older thread running under all of this too, one most people never hear about. Decades before any of these electric imports crossed the Pacific, a Tokyo-born engineer named Hiroshi Hiraoka had traveled to Philadelphia in the 1880s, specifically to study rolling stock construction at the Baldwin Locomotive Works, and came home to found Japan's first domestic locomotive works in 1889. The instinct to learn by going straight to the source, rather than simply buying and using, didn't start with the electric locomotives of the 1920s. It was already a generation old by the time this story begins. That's debt number 2, paid. Here's the part nobody in Pennsylvania or New York had planned for. Chapter 3. 2 rivals, welded into one machine. Here's the debt from Chapter 1, finally paid in full. Building the machine that ended the imports meant marrying 2 systems that were never supposed to touch each other. Follow the actual chain of force, because this is where the real fight lived, invisible to anyone just watching the train roll by. Overhead, a copper wire carries 1500 volts of direct current above the tracks. A contact device on the locomotive's roof, a pantograph or a trolley shoe, depending on which builder's design you're looking at, skims that live wire and draws the current down into the machine's guts. From there, it has to pass through a circuit breaker fast enough to snap the connection the instant something goes wrong, because 1500 volts through a short circuit does not politely warn you before it kills. Surviving current then feeds traction motors bolted directly onto the axles, converting raw electrical force into mechanical torque, geared down to trade top speed for pulling power on a line full of stops. Fire the whole chain correctly, and 67 tons of American-built steel accelerates a loaded passenger train out of Tokyo faster and cleaner than any coal-fired boiler ever managed. Get one link of that chain wrong, and you have a 1500-volt short sitting directly beneath a crew cab, the same silent, switch-gated danger that had already claimed workers on the Pittsburgh factory floor before a single locomotive ever left for Japan. The circuit breaker was no minor component buried in a parts list. It stood as the one piece of hardware standing between an ordinary equipment fault and a fire that could take the whole locomotive, and the crew inside it, in seconds. Picture the scale of what these early imports actually were. The earliest Baldwin-Westinghouse pair, later reclassified as the ED-10, weighed 67 tons apiece, ran on a four-axle arrangement, and produced 1,100 horsepower combined from four separate traction motors, enough to move a loaded train at 40 miles an hour. Not an impressive top speed by modern standards. In 1922, on a rail network that had never run anything but coal-fired steam at meaningful volume, it was an entirely different category of machine. Quieter than a firebox, cleaner than anything burning coal in a tunnel, engineered by people 7,000 miles away who had never once seen the gauge, the climate, or the traffic pattern the machine would actually operate under. Other American classes followed in the same import waves. Designations like the ED-11 and ED-14 from the General Electric and Alco side, the ED-53 and EF-51 from the Westinghouse and Baldwin side. An alphabet soup of experimental hardware that Japanese engineers treated less like a fleet and more like a library. Now here's the actual impossibility buried inside Chapter 1's biggest debt. The Westinghouse and Baldwin machines and the General Electric and Alco machines weren't variations on one shared design. They were two separate answers to the same problem, engineered by companies that spent real money trying to outsell each other in every market where both showed up. Westinghouse and Baldwin had built their machines around a particular frame geometry and a particular arrangement of electrical apparatus, a configuration that had proven itself rugged and easy to service in the field. General Electric and Alco, meanwhile, had engineered something else. High-speed circuit breakers considered the sharpest safety technology on the market, capable of interrupting a dangerous current spike faster than the Westinghouse and Baldwin equivalent could manage. So which lineage do you copy? Japanese engineers didn't pick one. They took the circuit breakers from the General Electric and Alco machines, the fastest, safest switching hardware available anywhere in the fleet, and mounted them inside a frame built to the Westinghouse and Baldwin layout, the configuration their own maintenance crews had found easiest to service under real operating conditions. Understand what that actually required in practice. No shared blueprint existed for this combination because it had never been attempted before by anyone in either country. Nobody at General Electric had engineered their breakers to fit inside a Baldwin-style frame. Nobody at Westinghouse had built electrical apparatus expecting a rival's switching gear to sit inside it. Every dimension, every tolerance, every mounting point had to be measured directly off the imported hardware and translated by hand into a design that had never existed anywhere before. That kind of work has no shortcuts. It means pulling a breaker assembly out of a General Electric frame it was designed for, setting it against a Westinghouse Baldwin chassis it was never meant to see, and figuring out, through direct measurement, trial fitting, and repeated failure, exactly how the mounting brackets, the current-carrying bus bars, and the control wiring would need to change to make two rival philosophies of engineering agree to share the same steel. Get the fit wrong by fractions of an inch, and a fast-acting circuit breaker becomes a fast-acting circuit breaker that no longer breaks the circuit fast enough, sitting under a passenger cab at speed. That translation work fell to men like Seiji Mitsuida, a production engineer at Hitachi, who spent real hours with his own hands inside the imported machines, tracing wire runs and frame joints the original manufacturers had never documented for outside eyes to read. Years later, engineers involved in the project would describe the process plainly. As long as the imports kept running without trouble, crews simply drove them and never looked past the control panel. It was the breakdowns, the moments an American or European part couldn't reach Japan fast enough to matter, that forced engineers to open the machines further and actually learn what was inside. The design and manufacturing work for the eventual domestic locomotive was split across 5 separate Japanese firms: Hitachi, Mitsubishi Electric, Shibara Engineering Works, Kisha Shizo, and Kawasaki Shipyard, coordinated under the Ministry of Railways, because no single Japanese company in the 1920s held the full range of expertise needed to complete the fusion alone. Overseeing the entire reverse engineering campaign was a government railway engineer named Kiichi Asakura, A man who would spend the better part of a decade turning 59 foreign machines into blueprints neither American company had been asked to authorize. Here's the bigger question this should raise, and it's the one that ought to have worried anyone sitting in a Pittsburgh or Philadelphia boardroom around 1925. If a foreign government can buy your machine, take it apart, and build a better fused version without your input or your consent, what exactly are you selling when you sell a locomotive? A finished product? Or a lesson plan with a price tag attached, good for exactly as many years as it takes the buyer to finish reading it? Baldwin and Westinghouse didn't act worried. Why would they? They had a war-sized order book behind them, a client list stretching across nearly 80 countries by the late 1920s, and a business model resting on the comfortable assumption that overseas customers would keep needing American parts indefinitely. That assumption was already being tested by the same country that had just spent several years quietly proving it wrong, one dissected circuit breaker at a time. We still haven't answered the question sitting underneath everything so far. What did it actually cost, in human terms, to build the machines that ended up teaching an entire foreign industry how to outgrow them? The mechanics are settled now. The bodies aren't accounted for yet. Chapter 4. The Men Who Fed the Furnace. The imported machines had a maintenance problem that had nothing to do with engineering and everything to do with geography. When something broke in Japan, the replacement part was 7,000 miles away, on a boat that hadn't sailed yet. That distance was the real education, more than any blueprint. When the imports ran clean, crews simply operated them and moved on with their day, the same as anyone running unfamiliar machinery competently. It was only when something failed and the American or European supply agents couldn't get a replacement part across the Pacific fast enough to matter that Japanese engineers were forced to open the machines up themselves and actually learn what was inside them, out of necessity rather than curiosity. Every breakdown became an unplanned lesson. Every lesson made a fully domestic locomotive a little more inevitable and a little more urgent. Running the imports at all took a different kind of crew than steam ever had. There was no fireman shoveling coal, no boiler pressure to nurse, but there was a live 1,500-volt system that punished ignorance instantly and without a warning shot. Japanese crews had to be trained essentially from scratch in electrical operation, a skill set that barely existed inside the country's own railway workforce in the early 1920s. Engineers accustomed to reading a firebox by color and sound now had to read gauges and breakers instead, on machines whose internal wiring diagrams, where they existed at all, were often written in English and German rather than Japanese. That gap between what the crews needed to know and what anyone had actually taught them was its own quiet danger, separate from the machinery itself. Now cross back over the ocean to the plants where these machines were actually assembled, because the men making them were paying for the same technology in an entirely different currency. Picture a foundry floor at Baldwin's Eddystone Works on an ordinary working day sometime in the 1920s. Molten iron pours from a tilted ladle in a controlled, glowing stream, close enough to a worker's boots that a slip means considerably more than a burn. The heat radiating off an open furnace face doesn't register as weather. It registers as a wall you lean your whole body against, hour after hour, shift after shift. Overhead cranes haul half-finished locomotive frames through open air on chains rated for tons, and every man on that floor has learned, the hard way himself, or by watching a coworker learn it the hard way instead, exactly how far back to stand and exactly which sounds mean trouble is coming. This was routine. This was an ordinary Tuesday, repeated for decades. Put yourself on that floor now, at the tail end of a 10-hour shift. Your ears are still ringing from a drop forge hammer 3 bays over that never really stops. Your hands are raw from filing a casting seam smooth by hand, because the machine tools of the era still couldn't finish that kind of work alone. Samuel Vauquelin, the Baldwin executive who would run the company through the very years these locomotives shipped to Japan, had walked this exact kind of floor decades earlier as a young shop foreman, and it had left his own hands frozen into a permanent half-clutch from endless hours of chipping and filing metal by hand. He knew precisely what the work cost a body, because his own body had already paid a piece of that price before he ever climbed into management. Across the state, inside Westinghouse's East Pittsburgh works, the danger wore a different face entirely. No open furnaces on that particular floor. Instead, rooms full of high-voltage testing apparatus, transformers proofed under loads that could kill a careless man instantly and without warning. No flame, no smoke, just current waiting behind a switch. Across its working lifetime, that single plant employed something like 22,000 workers, building the switchgear, the traction motors, and the circuit breakers that would eventually end up, unannounced to the men who wound them, bolted inside a Japanese-designed frame on the far side of the planet. Here's a fact worth sitting with for a moment. Neither the Eddystone foundrymen nor the East Pittsburgh electrical crews had any idea their work was headed for a foreign autopsy table. They built to specification, shipped the order, and moved on to the next job on the schedule. The men doing the actual dissection, Asakura in the ministry's offices, Mitsuida on the Hitachi shop floor, never met the American workers, whose components they were taking apart wire by wire. Two sets of hands, on two sides of the widest ocean on Earth, building the same machine for completely opposite reasons, and never once exchanging a word. Step outside the noise for just a moment. On some mornings along the Tokaido corridor, before the electrified schedule took full hold, commuters still boarded steam-hauled cars in the pale half-light outside Tokyo, watching soot drift low over rice paddies that hadn't changed shape in a century of use. Within only a few years, that same stretch of track would carry 67-ton American-built machines humming quietly under overhead wire instead of roaring under a firebox. Nobody standing on those platforms knew they were watching the last steam-powered mornings of a corridor that would go on to define modern Japanese rail travel. It was just a commute. Until, one ordinary morning, it wasn't anymore. Back in Pennsylvania, danger wasn't limited to the shop floor either. It lived in the balance sheet, too. Baldwin's own president, in 1919, approved nearly $7 million in locomotives, shipped to a newly reborn Poland, entirely on credit, at a moment when Baldwin's own board considered the decision reckless in the extreme. Post-war Europe was a gamble. A customer that couldn't yet guarantee its own borders was a worse one. It took a full decade, but Poland repaid every dollar of principal and interest, the final payment landing in 1929, on time to the letter. Baldwin's appetite for risk overseas reached well beyond Japan. It was company culture, baked in at the top, and it had already nearly bankrupted the firm once before, back in 1907 and 1908, when the workforce collapse from 18,000 men to under 5,000 nearly took the whole enterprise down with it. The danger inside Baldwin's gates wasn't only mechanical either. In the same era, 13 separate craft unions organized across the workforce, and when a slowdown in orders led management to announce layoffs aimed squarely at union members, the men walked. Labor claimed 10,000 of 13,000 workers had struck. Company records told a different story, insisting more than half the workforce had stayed at their posts. Vauclain offered strikers their jobs back individually, on his own terms, and refused to reinstate the organizers who had led the walkout. Many returned anyway. Union cards surrendered at the gate. The strike broke. It was a different kind of danger than a furnace or a live transformer. The danger of a paycheck disappearing without warning, or a union card costing a man his job entirely. But it was danger all the same, and it shaped exactly the kind of workforce that would go on to build export orders for a foreign government it had never heard of and would never meet. That's the quiet part of this whole story. No betrayal, no conspiracy, just an ocean's worth of distance. Two industrial cultures who never had to look each other in the eye, and one side finishing an education the other side never realized it was providing, until the danger caught up with everyone at once, on both continents, within the same handful of years. Chapter 5. The morning Building F went silent. April 10, 1917, just past 10 in the morning. Building F, at the Eddystone Ammunition Corporation's plant. The very same sprawling complex that would soon manufacture the mechanical frames Japan came to study just 5 years later, erupted in a chain of explosions that, to this day, no one has ever fully explained. 380 workers, most of them women, were inside that morning, packing shrapnel shells with black powder as part of the wartime munitions contract Baldwin had taken on to help arm the American war effort before its locomotive business mattered again. 18 tons of black powder propellant sat stored inside the building. Something set it off. The first blast tore Building F apart, followed by smaller detonations that sprayed the surrounding grounds with shrapnel bullets, meant for a battlefield an ocean away, not a factory floor in Delaware County, Pennsylvania. A fireman responding to the scene lost a leg in the chaos. Local hospitals filled past capacity within the hour, and volunteers poured in from the surrounding towns to help carry the wounded clear of buildings that were still smoking. Rescue crews and hospital staff worked through the rest of that day and into the night, treating burns and shrapnel wounds by lamp and daylight both, the wounded arriving faster than beds could be found for them. The blast pattern from the initial explosion, followed by the smaller secondary detonations, meant nobody could say with certainty how many workers had been caught inside Building F until the wreckage was cleared enough to search it properly, days later. By the time the fires were finally out, the death toll stood at 133. 55 of the dead could not be identified at all. The blast had left nothing behind to identify them by, and they were buried together in a mass grave at Chester Rural Cemetery. 12,000 mourners turning out for the service, Baldwin's own officers standing among the crowd. Samuel Vauquelin, addressing the disaster publicly in the days afterward, called it work that had been, in his own words, planned and executed by maliciously inclined person or persons. No sabotage was ever proven. The true cause of the explosion went into the ground, alongside 55 workers nobody could name. That is the fact we withheld back in Chapter 1. Hold it next to everything else you now know. The same industrial complex, the same workforce culture, the same production machine that would spend the next 5 years quietly building the mechanical bones of Japan's imported electric locomotives, had already buried dozens of its own people in an unmarked grave before a single one of those export orders ever cleared the yard gate. The plant reopened within weeks. Wartime output mattered too much to the national effort to halt production for mourning. By 1922, that same complex had pivoted back to its original trade, building mechanical frames for locomotives. Among them, the two Class 1000 units bound for Japan under Westinghouse's electrical work. The scars in the ground were barely 5 years old when the export orders that would eventually end up on a Tokyo autopsy table rolled out through the very same gates. 7,000 miles away, Japan's own breaking point was arriving on a slower fuse, but it was building toward its own kind of crisis all the same. The imported fleet kept failing in the field on its own schedule, and every failure that couldn't wait for a slow American or European part forced Japanese engineers to open the machines further, learn faster, and push harder toward full domestic manufacture. By 1925, the Ministry of Railways had committed formally to a domestic electric locomotive project. Hitachi had already gotten a running start 2 years earlier, completing its own Class ED-15 in 1924, using data gathered from close observation of the American imports. Proof, if anyone in Pennsylvania had been paying attention, that Japanese manufacturers weren't waiting for permission to start learning. By May of 1927, full-scale development began in earnest on what would become the Class EF-52. Originally specified as a freight locomotive, and then revised mid-development to handle passenger service as well, because the ministry realized it couldn't afford two separate domestic programs when it barely had the expertise to finish one. Failure here carried a different kind of danger entirely. Professional and national exposure at a scale that mattered to an entire industrializing country. If the jointly designed Japanese locomotive failed its first real tests, the Ministry of Railways would have spent years and a fortune proving publicly that Japan still couldn't build what it had just spent the better part of a decade dissecting. Asakura and the engineers working under him faced something bigger than a technical puzzle in a drafting room. They were staking a young industrial nation's credibility on whether a machine assembled from 5 separate companies' work, incorporating design choices cherry-picked from 2 rival American manufacturers who had never intended to cooperate, would actually hold together under real passenger traffic on the country's single busiest trunk line. It had to work on the first real test. There was no quiet way to fail in public, and everyone involved knew it. A failed domestic locomotive wouldn't just embarrass an engineering team. It would hand every skeptic inside the ministry and every foreign manufacturer watching from across the ocean hard proof that the entire 6-year dissection had been a waste of money and time, and that Japan's electric railway future still ran through Pittsburgh and Philadelphia, whether anyone in Tokyo liked it or not. That's the second staircase this story climbed, this one leading toward independence rather than toward an explosion. Every imported breakdown Japanese engineers couldn't afford to wait out was one more reason the ministry couldn't keep depending on the 59 machines that had taught them everything they knew. The unreliability that made the imports frustrating in daily operation was the exact same unreliability that made a domestic locomotive unavoidable. Chapter 6. The Empire that Learned to Build Its Own Bones. May of 1928. The first-class EF-52 rolled out of Hitachi's works under its own power, the product of full-scale development that had only begun a year earlier. In May of 1927, Asakura and his engineers put the machine through initial performance trials before allowing full production to proceed. The first time a fully Japanese-designed mainline electric locomotive had ever been asked to prove itself on the country's busiest stretch of track, the same corridor where the American imports had spent 6 years quietly being measured, wired, and copied. There was no ceremony built to survive in the record. No printed program, nothing but a machine either holding together under real load or not. It held. This is the moment this entire video has been walking toward. Japan hadn't just imported American locomotives. It had studied them, cut them open, borrowed the safest switching technology from one American rival and the sturdiest frame philosophy from another, and welded the result into a machine that neither Westinghouse, nor Baldwin, nor General Electric, nor Alco had ever built, or even imagined building together. 9 units of the class EF-52 were completed between 1928 and 1931, split across 5 different Japanese manufacturers, working from a single ministry-coordinated design. The locomotive proved reliable enough, fast enough, and rugged enough to become the railway's standard express passenger machine on the very corridor the American imports had once dominated. Those imports were quietly retired from frontline express duty, their job finished the moment they had finished teaching it. Seiji Mitsuida, the Hitachi production engineer who had spent months with his hands inside the imported machines tracing wire runs nobody had documented for him, stayed with the domestic electric locomotive program well beyond the EF-52's debut. Part of the generation of Japanese engineers who went from copying foreign hardware to training the next generation of Japanese engineers in turn. Kiichi Asakura, the government engineer who had overseen the reverse engineering campaign from the ministry's side, lived to see his design run for decades before his death in 1978, long enough to watch the country he had helped electrify go on to build the Shinkansen, the fastest railway on Earth, at its debut in 1964. running along a corridor that in places still traces the same ground those first imported locomotives once covered. Samuel Vauquelin never saw any of it unfold from the other side of the Pacific. He died in February of 1940, having spent his final years as chairman insisting publicly that steam locomotives would dominate American railroading for decades yet to come. That prediction aged badly on two separate continents at once. Diesel power gutted Baldwin's own business within a generation of his death, while the Japanese electric program he'd unknowingly helped seed went on to outdevelop the very imports his company had built. So where does everything in this story actually stand today? Baldwin's Eddystone Complex, the 616-acre site that built the ED-10's mechanical frame and buried 55 of its own workers a handful of years earlier, stopped producing locomotives for good by the 1950s. Demolition crews spent 53 weeks tearing the buildings down starting in 1994. Where the erecting halls once stood, you'll find retail development today, a century of industrial history flattened into parking lots and storefronts. Westinghouse's East Pittsburgh works fared only slightly better. The factory floor where engineers once tested transformers under lethal voltage sat empty after the plant finally closed for good in the 1980s, gutting the surrounding town along with it. But the buildings themselves survived, redeveloped into a multi-use industrial park. And today, part of that very same floor space, under cranes that once hauled locomotive components through open air, belongs to a company manufacturing zinc batteries for renewable energy storage. The circuit breakers bound for Japan are long gone. The floor that built them is still, a century later, building something that carries current. And the machines themselves? One of the original 1922 imports, Class ED-10, the very first Baldwin Westinghouse export, survived in active revenue service, under a different owner, all the way until 1986, longer than almost anyone who built it ever lived to see. It sits preserved today at a small depot outside Tokyo, restored to its original livery, 67 tons of century-old American steel standing quiet under a foreign sky it was never designed with in mind. And the first-class EF-52, the machine born out of the autopsy, the locomotive that finally made the imports obsolete, stands today inside the Kyoto Railway Museum, under a roof, nameplate polished, walked past daily by families, with no idea they're looking at the finished product of a 6-year international dissection. The design didn't stop evolving once the imports were gone. Successor classes followed through the 1930s and into 1940, each one an improvement on the fusion Asakura's team had first proven. Gear ratios retuned for more pulling power without sacrificing top speed. Output climbing from around 1,350 kilowatts on the original EF-52 to 1,650 kilowatts by the time the last of that lineage entered service. Within a decade of buying its first foreign locomotive to dissect, Japan was iterating on its own design faster than it had ever managed to import foreign ones. Nobody who built the originals in Pennsylvania or Pittsburgh ever saw either preserved machine in person. The men who forged the frames and wound the coils shipped their work across an ocean and never learned what became of it afterward. The men who took that work apart on the other side never met the hands that built it in the first place. Two industrial cultures, one export order, and a lesson that outlived every single person who was in the room when it started. Other pieces of this story still stand too, if you know where to look for them. Up in the mountains west of Tokyo, at a heritage park built on the site of a former motive power depot, preserved electric locomotives from Japan's early import era sit on display for visitors who mostly come for the mountain scenery and leave having learned, almost by accident, how much of their country's railway history was built on hardware bought second-hand from people who never expected to be studied that closely. They don't build empires like that anymore, quietly, out of somebody else's inventory, one dissected machine at a time. But for roughly 6 years in the 1920s, That is exactly how one got built, on the far side of an ocean, out of parts two American rivals never meant to share, by men on both continents who never learned each other's names.